bolts of how to get right. Oh, is it started yet?
Yeah.
Okay, I got to teach you the nuts and bolts on how to get right answers on logistic growth problems, and then we're going to do the AP Calculus flu epidemic, and it will be fun. But first, let's go ahead and do the math of logistic growth. Okay. The only thing you need to remember now, or not the only thing, but the biggest thing you're going to need to remember is this idea that if you got logistic growth, then you have a differential equation where the absolute rate of change of a population is proportional not only to the amount of population you have, but it's also proportional to the, and don't write this down if you mind, don't mind, oops, of course I wrote it wrong. Don't write this down, okay? But I want to just remind you conceptually that the absolute rate of change of a population is proportional not only to your population, but also proportional to the difference between the carrying capacity of the population and the population. So you might think of it in terms of the rate of change of the number of people who have the flu is proportional not only to the number of people who already have the flu, but also proportional to the number of people who have yet to get the flu. You see, the more people who have yet to get the flu, the more people you can get getting the flu. And it's that way, you know, for a rumor, the proliferation, the number of people who, you know, hear a rumor in any given day is proportional not only to the number of people who already know the rumor, so they're more likely to spread it, but it's also proportional to the number of people who have yet to hear the rumor. So you can have lots of new people hearing the rumor. You see what I mean? And it's that way, like I said, for any sort of logistic growth thing. But the weird thing is we factor out the M mathematically to make it more easy to deal with mathematically. We factor out the M, and then we combine the K and the M into one big constant that we call K. Okay? So go ahead and write this down. This is the equation we're actually going to be dealing with, even though it's not as obvious to me now that dp dt is proportional both the p and also the difference between p and the carrying capacity. Okay, and if this is your differential equation, then this ends up being your solution. P of t ends up being the carrying capacity divided by 1 plus a e to the negative kt, where a is equal to the carrying capacity minus the initial population over the initial population. And again, I'm going to show you how to do this in Chapter 8, which is next semester, so you're just going to have to believe me now that that's the solution to our logistic growth differential equation. All right, and we were in the middle of doing a problem where I was asking you to find dp dt, find an expression for P of t, make a slope field, and I wanted the population to be between 0 and 1.25 times the carrying capacity. And then part D, draw the solution curve. Okay. These are the problems that we started yesterday, or the problem that we started yesterday. And so I gave you number 1 where I said, hey, K is equal to 0.04, the carrying capacity is equal to 100, and the initial population is equal to 10. And we had discovered the following. Part A, we got an expression for the differential equation, dp dt equals 0.04 times p times 1 minus p over 100. That was my differential equation. We got an expression for the solution. The solution ends up being 100 over 1 plus e to the negative 0.04 t, and then we found what a was, and a happened to be, for this problem, a happened to be 100 minus 10 over 10, which got me 9. So this was a 9. And then part C was to do the slope field. And I wanted your slope field. So this is from 0 to 1.25 m, so this is 100, which is my m. And so this is 50, this is 25, this is 75, and then this is 125, because I wanted you to go all the way up to 1.25 m. It turns out, let me ask you this question now, and now I'm gonna stop talking to myself and ask you guys, which of these equations do I use to make my slope field?
B.
A.
A, correct? A. I use the differential equation to make the slope field, because the slope field is a bunch of slopes, and this is the slope. So I just want you to see, learning the logistic growth, it is equally important to know the expression for the differential equation as it is to know the expression for the actual solution, because sometimes you want to do a slope field of your logistic growth, so that you can see what many different solutions look like. So anyway, let's go for it. And so we decided, we see that it's going to be the same slope for every y value. So we did p equals 100. And when p equals 100, your dp dt is going to equal 0.04 times 100 times 1 minus 100 over 100. And so I hope you see that that equals 0, right? So at 100, my slope field is going to be 0. My slope is 0. By the way, when you get a bunch of slopes that line up like that, what does that end up always being? Yeah, an asymptote. An asymptote, absolutely. Yeah. Okay, I was going to say a joke, but since I'm being videotaped, I can't say it. So here we go. Let's try p equals 50, okay? So I need my dp dt to be 0.04 times 50 times 1 minus 50 over 100. And so 50 times 0.04 is 2, 2 times a half is 1, I get 1. So my slope at 50 is going to be 1. Let's go ahead and do it for 75. dp dt is going to be 0.04 times 75 times 1 minus 75 over 100. 0.04 times 75 is 3. 1 minus 3/4 is a quarter, so I get 3/4. So this slope is going to be a little bit less. If that's 1, then maybe we'll make 3/4 look less, I'm not going to break out the protractor and try to make it all perfect. Okay. And how about 25? I hope you see it's going to be symmetrical. At 25, we got 0.04 times 25, which is 1, and then 1 minus 1/4 is 3/4, so you get 1 times 3/4, which is 3/4 again. So this is going to be a smaller slope as well. And then finally, how about 0? What's dp dt? What's dp dt at p equals 0 going to get me?
0.
Yeah, 0. So I'm going to, and I hope that makes sense, right? Why does it make sense that if your population is 0, you're just going to stay at 0?
Because there's no logistic.
Yeah, there's nothing there. It's like the population of dodo birds, right? Right now, the logistic growth curve for dodo birds is that guy, because there ain't no dodo birds. Okay, and then finally, let's go for p equals 125. Okay, so dp dt at p equal 125, alrighty, that's going to be 0.04 times 125 times 1 minus 125 over 100. So this is going to be 5 times negative 1/4. That's negative 5/4. So these guys are negative, and they're a little bit steeper than the 1. Okay, so there's my slope field. Let's go ahead and make the solution curve, and then we'll talk more about this slope field. I need to start at 10, right? Because here, I'm going to start at 10. Oh, this guy's kind of messed up. Let's see if this guy's any better. So I'm going to start at 10. And your slope is 0 here, your slope is 3/4 here, so you can kind of assume the slope is somewhat between 0 and 3/4. Then you get to 3/4, then you get to 1, then you get to 3/4, then pretty soon you get to this horizontal asymptote, and your growth levels off. And that would be your solution curve for P naught equal 10. Because this asymptote is going forever and ever and ever. Do you notice that my graph starts off looking like exponential growth, but eventually levels off? Looking at my differential equation, why would my graph look like exponential growth when P is really, really small? What happens to this equation when P is really small? What does this equation look like? What is it approximately the same as when P is super duper small? Like, say again?
PT.
Yeah, or PT, or you mean KP? Yeah, that guy. You guys okay with that? When P is small, when P is way, way less than the, and here's two facts, okay? Two facts about logistic growth. First fact, when P is way, way less than M, then your dP dt approximately equals Kp, right? Because your 1 minus P over M, this guy is approximately equal to 1, right? Because P over M is approximately equal to 0. When P is way, way less than M, then this guy here is approximately equal to 0. And so this term gets to be 1, and so I just get dP dt is approximately equal to Kp. You see, what type of growth do you get with just dP dt equals Kp? Say again? Yeah, thank you very much, Chris. Exponential growth. So I want you to see that initially with a logistic growth situation, you start off with exponential growth, okay? Now, the second thing I want you to notice is there's an actual inflection point in the solution curve. And at what population does it appear that the inflection point actually occurs?
50.
Yeah, at 50. In fact, always, your inflection point for logistic growth will occur at half of the carrying capacity, when population is half the carrying capacity. That is, you get an inflection point when the population is equal to 1/2 the carrying capacity. And the special thing about this inflection point is that's when dP dt is at its maximum. That inflection point, dP dt is at its maximum, then the curve starts bending. dP dt is maximum at the inflection point. As a mathematician, I was really happy when 8 years ago, ex-President Obama was doing healthcare, the Affordable Care Act, and he said his goal was to bend the curve. And what he was addressing was the fact that healthcare costs were rising exponentially, right? And so his goal was to institute a national healthcare plan, which every other country in the world, every other developed country in the world has it. So every developed country in the world, their healthcare costs are half ours and their outcomes are better than ours. And so President Obama tried to do the same thing, and he did. He got the Affordable Care Act, and sure enough, it bent the curve. The exponential growth of healthcare started to level off. And so it was incredibly successful. And that's why, that's why we're trying to get rid of it now. Because this is America. And anything that really succeeds, we always try to get rid of. Always try to end it. So anyway, that's the two facts about logistic growth. At the start, it's always exponential, and at the inflection point, that's where you get your maximum dB/dt. Let me ask you one more question. What if my initial population was up here, higher than the carrying capacity? What's going to happen to that population? Yeah, it's going to, now is it going to die out? No, it'll just naturally fall to the carrying capacity, okay? And so there, of course, there's no inflection point, it just falls to the carrying capacity. And so this is the sort of thing that can happen, unfortunately, when the carrying capacity of an environment radically changes, right? Like let's pretend, this is something that's not true at all, it's a complete hoax, but let's pretend that the temperature of planet Earth is getting hotter, okay? Let's pretend that it's getting really, really hot. Well, what's gonna happen is you're gonna get a lot of countries in the hottest part of the Earth that are gonna start getting so hot that their carrying capacities are gonna fall. And when you've got a population, up here, and then suddenly the carrying capacity falls, now you're going to get die-off. You're going to get people dying off, And that happens to a lot of countries, but right now, it's not happening entirely due to environment, right? Why do countries get great losses of population nowadays? What's the biggest thing that causes countries to lose a bunch of their population?
Disease.
No?
Immigration.
Yeah, war. It's always political. War. Right now, war. Why did the population of Syria fall by like 33% or something? Because of that big civil war. Why did the population of Iraq fall? Because of their war, because of us, conquering Iraq, and so on. Why is Afghanistan having trouble getting population growth? Because of their wars. And so right now we're living in a time when war is the biggest reason why carrying capacities fall, and then you get these millions of refugees streaming out of the country because the carrying capacity of the country has fallen, but the carrying capacity fell not due to disease or climate issues, it fell just because of war, just because of political issues. Okay, well hey, it's time for you guys to do a problem. So here's what I want you guys to do. Let me erase this. And I think we'll get to the AP Calculus flu epidemic tomorrow. I want you to do A through D for this problem here, number 2. Your K is going to be 0.03, your M is going to be 200, and your initial population is going to be 100. So please do A, B, C, and D for those numbers. K equals 0.03, M equals 200, P not equals 100. And then I'll quote unquote help you. Okay, have you done part 8? No. Stop that. Do my stuff. Yeah, there you go. Okay, it's that easy. But I need you guys to go through the process. Great. Yeah. That's simple. Now you're ready to make your slope field. Yeah, you can call that 1 if you want. Oh, just, that's 1, but yeah, you did fine. No, you did fine.
Mr. Shannon,
Yeah, it is.
where do you want us to make our slope field to?
The same as what it says there, so 1.25 M. So in this case, you're gonna have to go up to 250. And you know, the time doesn't matter, because T is not in the differential equation. Yeah, there it is. Cool color. Okay, great. Maybe a larger slope field would be better. I don't know. That's pretty microscopic. Good. Here, a little bit more work. Making it a little dots for yourself. Great, perfect. Now your differential, okay, you're already plugging in. Where's your differential equation? Okay, yeah, I want to see dV equals K times P times 1 minus, M over K. I want to see that differential equation. That's going to be one of the answers I'm looking for on the next test. I need to see that in the answer column. Yeah, that's beautiful. Okay, looking good. So far, so good. Now plug in those numbers, D. 9/8. Okay, you guys getting something that looks like that?
Yeah.
Okay. Yeah, this would be the inflection point, except tell me, at what population is my inflection point going to be in this graph?
It's 100.
Yeah, population 100. When your population is half of your carrying capacity, you're going to be your inflection point. So since my initial population was at 0, I don't get to have that bend, obviously, because essentially that's my inflection point. But yeah, there you go. And if your population is above 200, you fall to 200. So hey, that's logistic growth. I need to show you a couple of algebraic tricks now so that you can do your homework, and then tomorrow we'll do our great AP Calculus flu epidemic, where we actually see in real life that we do this random process, and it turns out that the random process ends up having a logistic growth model. You'll see. It'll be fun. No. Oh, I mean, I don't know. Someone may have done this before, I'm sure. I mean, I learned it from a guy. Okay. Hey, here's some algebraic trickery that I need to show you. Algebraic trickery. Okay. Find K and M. Here, what if I gave you this? dp dt equals 0.02p minus 0.0002p squared. And I said find K and P. Well, to find K and P, you're going to have to factor it and make it look like that.
Yeah.
So what are you going to factor out?
0.02p.
Okay, hey, let's do that. Let's factor out 0.02p. If you're thinking factor out p, that's fine as well. The key is, I need to get a 1 there. I need to get a 1 there. That's your key. That's your goal. So yeah, you're going to factor 0.02p out. So you get 1 minus 0.01p, like that. Is that okay? Is 0.02 times 0.01 equal to that? 1, 2, 3, 4, yeah. Yeah, so it is. Okay, great. And then finally, I need it to look like this. I can't have 0.01p. I need to have the m in the denominator. How do I find what my m is? Okay, or how about just get the reciprocal of 0.01?
Yeah.
That is 0.01 in the numerator is going to be the reciprocal of 0.01 in the denominator. And the reciprocal of 0.01 is 100. So this ends up being 0.02p times 1 minus p over 100. And now you've got your k, 0.02, and you got your m, 100. So that's just the algebraic trickery. If they present it to you like this, then just make sure you divide by whatever so you get a 1 there. And if you've got a number multiplied by p, get the reciprocal of that number and put it in the denominator. So that's the first algebraic trickery you're going to have to do. The second one is just recognizing your solution. So I got 500 over 1 plus 50 times e to the negative 0.02t. Hey, you tell me, what's my carrying capacity?
500.
Yeah, 500. That's the formula. And what's my K?
Negative 0.02.
Yeah, just 0.02. You see that? In fact, from this, you could even find what your initial population is, right?
Yeah.
Because you know A is equal to M minus P naught over P naught, alrighty? And my A is 50 and my M is 500. So go ahead and cross multiply and solve for P naught. I'm not going to ask you to do it right now, you know, although there's something in me that can't help but try to do it, but I'm going to resist. I know you can do that. Okay, so just remember to be able to look at the solution. And I'm going to skip that. And then finally, in our remaining 2 minutes, I need to show you something other than logistic growth. Something other than logistic growth. dp dt. What if I told you that I had a population whose absolute growth rate was given by this equation? So the absolute growth rate is given by that equation. You guys okay with this? This is the last thing we're good doing together. Tell me, if my population equaled 2,500, is my population going to grow or decay? Am I going to gain population or lose population if my population was 2,500, according to this equation? How would you make that determination?
Multiply out.
Yeah, is anyone thinking stick in 2,500? Just stick in 2,500. You stick in 2,500, tell me, is my dp dt positive or negative?
Positive.
Positive. So what does that mean for my population?
It's gonna grow.
It's going to grow. So I guess it'll grow to infinity. Who can say it's going to grow? Okay, let me ask you this. What if my population was 1,000?
It's gonna decay.
Good. It's going to decay. You guys okay with that?
Yeah.
Because if I stick in 1,000, I got a negative. But here's my last question. What is it going to decay to? To what particular population? Does it go to 0 or does it stop on its way to 0?
It stopped on its way to zero.
Good. What population is going to stop?
500.
How'd you know that, Daniel?
I kind of just took 500.
Yeah, because when your population reaches 500, what's dp dt? 0, no more change. You see? So it decays to 500. Alrighty. Well, thanks a lot, and good luck, you guys. Good luck on tonight's homework.